A2 Further Maths, Planes and Angles. Now if you take any two planes in 3D space, and as long as those two planes aren't parallel or identical to each other, they must cross somewhere within that 3D space. It's exactly the same as in 2D. If you had two lines will cross somewhere in 2D space as long as the lines aren't parallel. So there's one plane, another plane will come through and cross it just there along that line. Let me just get my highlighter. There we go. So we can see they're clearly crossing just there. Now, if you take the normals to each of those planes, so if we take the normals to this plane, we can see it goes up at 90 degrees. So that's the normal for plane 1. And the normal for plane 2 goes across there. Okay, now if we just investigate the angle between those two normals. So those two normals come up here and they form this angle just here, as long as you've got them to cross. And what's important to notice is that angle just there is exactly the same as the angle between the two planes. That's very difficult to find the angle between the two planes if you don't use the normals. So what is the best idea to do is to find the two normal vectors, which is relatively easy if you've got the equation of the planes. And then if you find the angle between those two normal vectors, then it's always exactly the same as the angles between the two planes themselves. So how do you find the angle between two vectors? Well, you can use the dot product. So the dot product, A dot B equals mag A mag B cos theta, where the cos theta is the angle between the two lines, can be used to find the angle between the two planes. So the angle between the two normals, so the scalar product between the two normals is equal to the magnitude of one of the normals, magnitude of the other normal, cos theta. So let's have a look at an example of this then. So I want to find the acute angle between these two planes. That plane there written in vector form, and this plane here written in Cartesian form. So I'll give you a chance to write it down in your notebook. You might want to pause, you might want to have a go yourselves using the previous formula, and then you can check from my model solution. Okay, so let's see how far you got then. So the first thing I'm going to do is find the normal vector of these two planes. So I'll find the normal vector between those two. Starting with this one just here. So this first plane, I'm going to have to do a little bit of work. I'm going to have to find the normal vector by using the two directions of that plane. So there's a vector on the in the direction of the plane. There's another vector in the direction of the plane. And if I find a normal between those two, that will be the normal of that plane. So A cross B, get the cross product, and minus 9, 5, minus 6 will be a normal vector to that plane. If I try doing the dot product with both of those, you'll see it equals 0 because it's perpendicular to both of them. This one a lot easier. As you know, in the Cartesian form, the 3, the minus 2 and the 6 is your normal vector, just the coefficients of x, y and z. So there we go. I've got a normal vector there, I've got a normal vector there. Now, because I want the acute angle between the two planes, or just the angle between the two planes, what I can do is I can find the angle between the normal vectors. If I find the angle between the normal vectors using the scalar product, then it should find me the angle between the two planes as well. So I use the two normal vectors, I fill it all in, do all the number crunching, so I can work out that part by just times the cross, as you know, and there's mag A, mag B, cos theta. So the only thing you don't know is cos theta, so a bit of rearranging, and out pops this angle just here of minus 0.875. So once I've got that, you'll notice that I get an angle of 151.1 degrees. Now, I don't blame you for stopping there and thinking that's it, I've got the angle between the two planes, and it is the angle between the two planes, but don't forget it's asking for the acute angle between the two planes. Now, by their very nature, you're going to end up with both an acute angle and an obtuse angle between any two planes, unless they cross perpendicular, in which case they'll both be 90 degrees. But anything else will always have an obtuse angle and an acute angle. So you need to be wary. In this case, it's found the obtuse angle for you. How do you find the acute angle? You just do 180 minus 151.1. So the other angle would be 28.9 degrees. Okay, so we want to take any plane and any non-parallel line. We don't want a line that's parallel to the plane. So there's my plane, and there's a line that goes through my plane. All right, so it sort of spikes straight through it there. Okay, what I'd like to do is I want to find out the angle between the plane and that line. I want to find the smallest possible angle between them. So how do I do that? Well, the problem is you don't have a direction vector for the plane. This direction vector is very, very difficult to find. So because we haven't got that direction vector to find this smallest possible angle, if it's in a different place, it would get a bigger angle. You see, you're looking for the very smallest angle. So what you would use is not that bit at all, but use the normal vector. If we find the normal vector to the plane, then that's going to help us work out the angle. So although this finds us something we don't want, the angle between the direction of the line and the normal vector, it can be used to find the angle between the direction of the line and the plane. So how do I go about doing it? So as long as I've got the normal vector of the plane, and as long as I know the direction of the line, I can work out the angle between them. And then once I've got the angle between those two, I can easily find the angle between the line and the plane by taking it away from 90 degrees. So the angle between the normal and the direction of the line, using the scalar product again, same as we did before. Anytime they ask you to work out an angle between things, you should be thinking scalar product. So find the angle between those two. Once you do, take it away from 90 degrees. So we're going to have a look at an example of that then. So the angle between the plane and the line in Cartesian form. In fact, they're both in Cartesian form. So again, write down your notebook. I can pause, give you a chance to have a go yourselves. Okay, so let's see how far you would have got then with the model solution. So the first thing I want to do is find the normal to the plane and the direction of the line. So the normal to the plane is going to be 1, 2, minus 4. So hopefully you got that. This is just the coefficients of x, y, and z. The direction of the line, be very careful when you have it in this form. You want to be thinking about making sure that you've got the x, y, and z in the right place. So I can see x is okay, so it's definitely going to have 2. Y is okay, so it's definitely going to have 4. And z minus 1 is over 1, so we've got 1 there. So the direction there would be 2, 4, 1. Just be wary in case these two are the other way around, and you have a minus number. Now find the angle between the two vectors. So if I find the angle between those two, I can use my dot product formula again. Notice I've rearranged it already. So the dot product, mag A, mag B, cos theta. So I've rearranged it to get that. Gets me 0.2857. So therefore my angle is about 73.4 degrees. And as before, don't stop there. That's the angle between the normal and the direction of the line. It is not the angle between the plane and the line. So what do I need to do to finish it off? To find the angle between the plane is do 90 degrees minus that bit. And so therefore we get 16.6 degrees. Okay, that's the minimum. So what I'd like to do is just have a quick go at the exercises on 5D and have a go at most of those because they get progressively harder and it will put you in a good position to be able to answer those types of questions in that exam. Okay, so I want you to take any two planes that are not parallel or identical and they must cross. So it's exactly the same as what we just said earlier on at the start of the previous bit. So there we go, they must cross. And we talked about taking the two normals, the same as before. There we go, two normals. Now last time we were looking at the angle between them, but this time what I'm going to investigate is the normal of those two normals. All right, so there's my two normal vectors coming off at 90 degrees. Now if I find the normal of those two, so where they cross, if I find the normal to both of those, what I'm going to end up with is a line that comes down here that is at 90 degrees to both of those. Okay, so two normal vectors, and then this bit here is the normal of those two normals. So it's the normal of the two normals. And that's what you actually call it, the normal of the normals. So the direction vector, and this is what's important, is always exactly the same direction as the line of intersection. Those two are always in exactly the same direction. So if you know the two normals, and you know the normal of the normals, then that can be used for the direction of the line of intersection. It's quite a helpful tool if you're trying to figure out the equation of the line, because then all you need is any point, any coordinate, like you see there, that lies on both planes, and that will give you the line of intersection. Okay, so we're going to have a look at an example then. So I want to find the line of intersection between the two planes, both of them in Cartesian form, and I want to find the line that intercepts both of those. So again, you can pause, you can have a go yourselves. You saw the previous bit, find the normal of the normals, find a point on either plane, on both planes, sorry, and see if you can find the equation yourself. Okay, so let's have a look at the model solution then. So the first thing you want to do, same as we've done a few times now, is find the normal of both of those. If you ever sat not sure what to do in an exam, always just find the normal of the planes, because there's a good chance that you need that, and there's a good chance you'll get some marks for doing it. So the normal of this plane is going to be 2 minus 1, 3, and the normal to this one is going to be 1, 0, y, 5z. So 1, 0, 5. So there we go. There's number 1 and 1, 0, 5 for the other one. You ignore the 7, we ignore the 5. Once we've got our two normals, what I want to do now is find the normal of those two normal vectors. So there we go. Find the cross product for them. Cross product, however you want to do it. Okay, so I expect you'll be able to find the vector product now. Equals minus 5 minus 7, 1. I can't simplify that, so it's fine to leave it as it is. Now what's important is that the direction of the line of intersection, so these two planes, the direction of them both is exactly the same as the normal of the normals. So that is my B value, just there. Now if I can find an A value, I can then write the equation of intersection. Right, the equation of the line of intersection. I can write it in the form A plus lambda B. So what do I get? I need to find a point that lies on both of these. So it's not as easy as just rearranging, make x a subject and then substitute it in, because that's going to end up with another equation with y and z in. But don't forget, you're only finding a single point that works. So you could use a bit of bit of guesswork and think, yep, I can see a value that works for both of those. Or maybe you want to do it more systematically. The best way to do it, to make it as quick as possible, is to set x, y, or z equal to 0. It cancels one of them out. So what I'm going to do is, for example, let x equal to 0. Straight away, if x equals to 0, then you can see that z would have to equal 1. 0 plus 5 times 1 is 5. Now once you've got z equaling 1 and x equaling 0, then you go back to this equation, and then you could find what y equals. So if that equals 0, that equals 1, take that away, y is going to have to equal minus 4. If you choose, let's say, x equals to 0 and then it doesn't work out nicely, maybe you've got two equations that don't really work, then what you can do is you could just change it to a different letter, just change y equals 0, for example. All right, so if I've made y equal 0, you can see then that you end up with two equations with x and z in. You can solve them simultaneously. That will be okay. Okay, right, so there we go. I've got an a value, 0 minus 4, 1. That is a single point that lies on both the planes. If I substitute it in, so now I've got that, I can now write my equation of the line. So A plus lambda B. And there we go. I found the equation of the line of intersection between the two planes. Now, if you've got three planes that form a sheaf, so we've seen this before, we've got three planes, they form a sheaf. There we go. So maybe you did a bit of work earlier, you found the equation 3, you found out they're consistent, so therefore they form a sheaf. So once you've done that, if they ask you to find the equation of that line, then what you can do is you could just ignore one of the planes. So ignore one of the planes and find the equation of the line between any two of them, and then that will be the equation of the line between all three. Okay, so I've got three questions for you to have a look at, and you need to be finding the point of intersection between the planar lines. So there's a plane just there in r dot n equals d form. There's your line in vector product form. Can you find where those two intercept? Can you then do it in this one where you've got in vector form and Cartesian form? And then can you do this one here where you've got a Cartesian form and a a vector product, well, a vector form, sorry. So can you find where each of those 3 lines cross with those 3 planes? I'm going to pause. You need to do the same. Pause it, have a go at all 3 of those, and then when you feel ready, press the play button and compare it to my solutions. So okay, let's see how far you got then. So when you're trying to find a point of intersection, it's all about trying to find an R value and substitute it into one of the other R values. Because remember, R is your general point X, Y, Z, and that's exactly what we're looking for. The point that's the same for both. So when is that X, Y, Z equal to that X, Y, Z just there? Now in this sort of format, like it's the moment, it's not very easy to substitute it in. So the first thing I'm going to do is just change this line into something we can actually use. Okay, we're going to put it into that vector form just there, because then we know that the x value equals -3 plus lambda. We know that y value equals 4 plus 2 lambda, and we know the z value is 3 on its own. And then when I got it in that form, I can now substitute it back into the original. So that's what I'm going to do. I'm going to substitute it into the original plane, because that's where the 2 values should be the same. And now I can expand it using the scalar product. So that's -3 plus lambda times by -3, that's there. 4 plus 2 lambda times by 6, that's there. And 3 times 2 will be 6, equals 12, same as that. Right, so the only unknown now is the lambda value. So if I expand it, there we go, I get lambda equals -3. And now that I've got -3, I can substitute it back into this equation just here, and that should give me my x, y, z value. So there we go, substitute it back in, put the -3 in where the lambda value is, and out pops -6, -2, 3. And that is the point of intersection, -6, -2, 3. You could check it in both of these. They should work. That one will get you 12 and that one will get you 0 when you find it. Okay, right, so if you want to pause again, now we've got the second one. If you didn't do it already, now you know what to do. Do that. Okay, so let's have a look at the second one then. So same idea again. We're going to change this into r equals a plus lambda b form, okay, in vector form, because then I can actually start to substitute it in. So I'm going to change it into that form, but notice I use a different parameter here, different variable t. I don't use lambda like I did on the previous one or on this where it says use it here, because the lambda's already been used in the first plane. Okay, so I have to pick something different. So I'll pick t. Also, just make sure that you're happy with where these bits come from. Remember, it's x minus a1 over b1, y minus a2 over b2, z minus a3 over b3. And it's written in this form because the b value is 0. That's why it's separate. It's not equal to it. This one I need to swap around. So it would be y minus 3. So therefore it's 3 all over -4. And this one's fine as it is. Remember, you're trying to get the numerators equal to 0. That's what you're trying to do. So 2, 3, 1 gets those equal to 0. Okay, so there's my plane in that form. Excuse me, my line in that form. Once I'm happy with that, I can substitute in the top line. And that's going to give me 3 things. It's going to tell me that 2 plus 5t equals 3 plus mu. There's no lambda value there. Just ignore my phone. I think I'm asking a question. There we go. So the second one, 3 minus 4t equals 12 plus lambda minus 2 mu. And then the bottom line, what does the z value equal? It's going to equal 1, no t's, 4 minus 3 lambda, no mu's. So that's quite handy. It's almost like I planned it to allow you to calculate the lambda first of all. Then once you've got the lambda value, then that might be able to use these two to somehow calculate the mu and the t value. But you're looking at triple simultaneous equations here that you can work with. Or if you want to, you can use inverse matrices to work it out as well. But it's a bit overkill in this case. So lambda equals 1 would work. 4 minus 3 gets you 1. Once we've got that one, then we can rearrange the first two to get those two equations, just to help us out. And then once we've got those two, You can use a function on your calculator if you want to, or you can do it yourselves however you want from school. We get t equaling 2 and mu equaling 9. Once you've got both of those and that one, you've got a choice now. You can either find the value by putting the t value back in, or you can find the point by putting in the lambda and the mu. Totally your choice. It doesn't matter which one you pick, you should get the same answer for both. So I've gone for putting 2 into there. I put 2 into there. 2 minus 5, 1 is going to be our point of intersection. If you tried putting in the mu and the lambda, you would have got exactly the same. You can see that 3 plus 0 lambda plus 9 times 1. Well, 9 and 3 make 12, same as that, and so on for the 5 and the 1. Okay, which is what I just said there. Okay, so again, I'll pause there for literally a little while and just give you an opportunity to do this one. I accidentally pressed the button, so I'll give you a head start and we'll see what we've got. Right, so it's already in a nice form just there. So what I can do is I can write the x, the y, and the z values like that. So I've got the x, y, and the z values. Now, if I know what the x, y, and the z values are, I could just take those values just there. I can substitute them back into the plane at the top, the Cartesian form. And now I'm back like I was in question 1. So that was with the scalar product. There we go. And so that tells me lambda equals -1. Once I've got the lambda equals -1, I can substitute it back into that one, and out comes the coordinate straight away. So the easiest and quickest one. Okay, so you know now how to find the point of intersection between planes and lines, and you're going to need those for some of the harder stuff later on. So it gives you an opportunity to practice some of those skills that you've just been doing if you go to exercise 5C on page 98. Okay, so last little bit, I want to take any plane I like and a point that's not on that plane. So there's my plane and there's my point floating somewhere above it. Now what I'd like to do is I want to figure out the shortest distance between that point and that plane, or the closest point. Now you'll notice that if we're talking about the closest point between there and there, it's always to do with the perpendicular. And you saw the same thing when we talked about skew lines, and we talked about where's the closest point between two lines, and it was the perpendicular part. So it's exactly the same. So I've got a point, I've got my plane, I want this closest point. Now what you should notice is actually, because this is 90 degrees going straight up from the plane, it's to do with the normal vector. The equation of the line, which we've got just there, which passes through the plane and through A, can be written down as A, which is just a point. So how to get from the origin to A, you should be given the point A, plus some amount of the normal vector. And that would give you a line that cuts through the plane and through the point A. And that line will also have the closest distance. I just need to figure it out. The point on that line, which is the closest point on the plane, is what I can figure out once I've got that line. I'm looking for where the line intercepts with the plane, which of course is what you just practiced. Where does that line, just there, intercept the plane itself? And that would get me the point P. Once I've got the point P, which is the closest point on the plane, which is what I was asking for up here, that's great, but sometimes you might have to work out the actual distance. So you can work out the distance by using the magnitude of AP. Okay, so let's have a look at an example of one of those, how to find the closest point on a plane. So I'm going to find the closest distance between the plane in Cartesian form, 2x minus y plus 3z equals 8, and that point. And as always, I'll pause, give you a chance to write down your notebook, and maybe to have a quick go yourselves before you write down the model solution in your notebook. And let's see what you got then. So the normal to the plane, 2x minus 6y plus 3z equals 8, is 2 minus 6, 3. Okay, just the coefficients on the front. Seen that plenty of times now. So that is the normal vector. The equation of a line through A that is perpendicular to the plane will be a point that goes through A, so that will be 3 minus 5, 7, in the direction of the normal. So therefore, I've got an equation of a line that is perpendicular to the plane, so therefore it will be the closest part of the plane to the line, but it also goes through my point A. Now what I need to do is I need to figure out where the closest point on the plane is. But the closest point on the plane is where the two R values will be the same. So I can work out the closest point A, finding where the intercept. So just to double check you're happy with this bit, x equals 3 plus 2 lambda, y equals minus 5 plus minus 6 lambda, and z is 7 plus 3 lambda. And I've substituted them into that top equation. So I've worked them out from there, substitute them into there. If I do all that, I can work out my lambda value. Lambda equals minus 1. And once I know my lambda equals minus 1, that's going to give me my x, y, and z for the closest point on the plane. There we go. So that's the closest point on the plane to the point 3 minus 5, 7. Okay, so the point 114. But the question is not asking just that, it's asking for the closest distance. But now I've got the closest point, 114, to the point 3 minus 5, 7. What I can do now is use a bit of Pythagoras' theorem in 3D. Work out the what each of them are squared, and therefore get 436.9 equals 7. So the closest distance between both of them will be 7, whichever unit is. Right, so the last little bit then, take any two parallel planes. There we go, two parallel planes. Now if you're looking for the closest distance between two parallel planes, it can be quite tricky to work it out because obviously there's lots of different distances. So the closest distance between two parallel planes will be the line that is normal, is perpendicular to both of them. But the way you can do it is by finding a point on any one of the planes. So if I just take this top plane, for example, and I figure out a point on that top plane, so it's just a point that satisfies the equation for that top plane, it doesn't matter what it is. So I found that point P. Now what I can do is I can find the closest distance between P and the plane underneath. Okay, by using the same skills that I did a minute ago, and what that will find for me is the closest point there on that plane to the point there on that plane, and therefore I can work out the distance. It's exactly the same as a point and a plane. Okay, it just seems more tricky. So that's it for vectors and planes. So what I'd like you to do, please, is have a go at the last exercise, 5e, on page 105. And that's all your vectors and all your matrices covered now.